So good afternoon, and my name is Nasir. I'm the Principal Engineer at CCAT. The topic of today's presentation is the digital thread and the digital twin, and more importantly, why is it important to you as a manufacturing companies? What value can you derive out of this? Why should you adopt it? And at the end, I'm going to talk about the programs that the state has made available to help you actually implement this technology by paying for a portion of it. So first off, let's define model-based definition, because this could mean a lot of different things. In the context of manufacturing, we're talking about a 3D CAD file with embedded product and manufacturing information. The change is from a 2D human consumable data set to a 3D machine consumable data set. What that does is the decisions that you would typically take to program your parts for CNC machining or for inspection or for welding, for sheet metal bending, even for floating, can now be encoded in software, so the software can do it for you because it sees the nominal information as well as the requirements, those features of the CAD model or the part need to be made to. Let's go through a couple of examples and existing softwares that you can purchase today that enable this production automation. So the first one up here, I'm going to talk about Siemens NX CAM. And what you see on the left, it's probably hard to see it on the screen there, but we have model-based definition. That's, again, the CAD model with the embedded PMI, product and manufacturing information. And on the right is an automatically generated CNC program. The way in which you teach NX how to do that, what decisions to make, what tooling to use, what strategies to apply to produce specific kinds of features are encoded in those 4 steps that are in the middle. So Siemens gives you the ability to set up CAM setup templates. It has feature-based machining built in, but any features that it does not recognize out of the box can actually teach it. And I'll show you at the end where we have a video repository that actually goes step by step, where a CAM programmer can follow along on the screen as to how you actually accomplish teaching NX how to, automatically generate a program. The other capability that just got embedded within Siemens is from a company called Cloud NC, and this is called CAM Assist for NX. Where I showed you in the previous slide that you have to set up or teach NX strategies. That is, if I have a hole, should I do a drilling operation? Should I do a single point boring operation? Should I do a circular machining path? The strategy depends on the size of the feature, the tolerance requirement, the material that the feature has, or that the part has to be made out of. But with CAM Assist, you don't even have to do that. It even takes away the need or the necessity for you to teach it strategies. With a single mouse click, as long as you have a CAD geometry right within apps, you launch CAM Assist, click a button, and it literally generates the entire CNC path for you. It does it for both 3-axis machining and 3+2-axis machining. So currently now available for 5-axis, but definitely works amazing for prismatic type parts. And then we have third wave production module, which is a machining optimization software. So if you add this in, and I'm going to show you a diagram of a digital thread workflow where you generate a CAM program. Now you can feed that CAM program into an optimization software so that it actually reduces your cycle time. Not only will it reduce your cycle time, but it optimizes feeds and speeds in such a way that you actually extend tool life and you get a better quality part out. It reduces vibration, chatter. It essentially gets rid of all the spikes in your machining program. So this is an example of a digital thread workflow where an OEM such as Pratt & Whitney would be sending over a model-based definition to you as a supplier company. And these are all the softwares and the workflow that you would follow to be able to consume that model-based definition. Again, at the end, we have a video repository that shows you step by step exactly how to accomplish this workflows. Other software such as SolidWorks CAM also have this built-in capability now. On the left, you have model-based definition. On the right, you have an automatically generated CNC program. And in the middle are your windows that allow you to teach NX the strategies that it needs to know to be able to come up with that program on its own. The function in SolidWorks is called color space machining. Let's look at inspection programming and how we can automate that with model-based definition. So here we're showing Siemens NX CMM module. This is a module within the Siemens software solution. And it gives you the ability to generate DMIS-based both. This is generic for any CMMs that are consuming DMIS-based code. So again, on the left, you have your model-based definition. On the right, you have the automatically generated CMM program. And in the middle are the functions that NX makes available to you for you to teach it the strategies. Again, you can set up a CMM template. That is your machine with the pneumatics. You have your link to PMI function, which is if you import PMI or you have a PMI model open up in NX with the CMM module activated, there's a button that literally says link to PMI. If you click it, it will read all of the requirements that each feature has to be made to, so long as it has PMI attached. And then it goes through the inspection method, which are the strategies that you had bought it. That it go through sequencing, which is optimization of the CMM pathing. And then you have the collision avoidance to avoid any part tool collisions. Another piece of software that you might be familiar with, PC-DMIS to program hexagon CMMs. On the left, you have model-based definition imported as a QIF file. That is a derivative model-based definition of a generic neutral format. On the right, again, you have the generated CMM program, and in the middle, you have your windows to teach you the strategies. Let's take a look at automated welding. This one's a bit more involved. There's a number of different software solutions to get you from a CAD model with the weld hollows embedded within that CAD to a robot rig welding off a program. The couple of pieces of the software that I'll show you in the workflow after this slide will kind of show you the entire digital thread workflow, but this particular case, we're relying on visual components to be able to import a QIF file, recognize the weld callouts on that file, and on import, so long as you have your virtual environment set, that is, you have your robot set up with any positioner, and you have your ported system set, literally you just import the QIF, and on import, it generates a robot welding program. So it will recognize start and stop for the weld piece. It'll also read in any of the parameters that you embedded within the weld comma. This is a typical workflow that you would follow for the automated welding workflow. So on the left there, if your customers are sending you either native CATIA, SolidWorks, NX, Creo, or QIF files in technical data packages in TDPs, then you can see the general workflow that you would use to consume that data, whatever file type it is. Once you receive it, you're gonna want to import that QIF into a software called NVIDIA. That's from CapVidia. And in that piece of software, you can generate a weld inspection report. Once you generate the weld inspection report, you export that weld inspection report out as a template inspection file, and you resave the QIF. That QIF that you resave out of NVIDIA gets imported into visual components. And as I said, on import, it generates the robot program for welding. And then what we're showing here, along with the welding process or the welding programming process, is the actual execution of that welding program with control feedback. So we're showing that weld program being generated for an ABB MIG welding cell. And that ABB MIG welding cell takes advantage of Fronius wire sense and seam tracking welding technology. So that program goes onto the AP robot, and the Fronius system takes over, and it actually does a touch off on the actual part, because there's always going to be a discrepancy between your idealized CAD, where a straight line is straight, and reality, where a straight line is never straight. So the Fronius technology will actually do a control feedback, find the actual edge, and as it's welding, it will track that edge, even if it deviates from its path, from the CAD path. From there, we can take it over to an M3DI scanner, a system that we have set up here in the front. We can take the scans on that weld, and then we can use Polyur software to extract the weld dimensions and populate that weld inspection template that we exported out of CAD technology. That can then go back into NVIDIA and hop into NetInspect. What I'm showing there is a full digital workflow, and no point is any data recreated, and at no point is there any person in the loop having to make any decisions, so long as those decisions that you typically make are taught to the software. So what's the value of the digital thread? What is the value that you can take away from this process? One, it's automation of production programming. It saves up to 80% of programming time. Typically, we see between 50 and 80%. 80% is literally an order of magnitude. So, and when I put it into perspective, 80% means that if it takes you weeks, it'll take you days. If it takes you days, it'll take you hours. So that's what I mean by Kaizen. It's a significant amount. It's not 5 or 10%. It's a significant amount. And then, by the very nature of the way these systems work, where you teach it strategies, you're capturing and encoding best practices for consistent programming. So whether you have an expert, right, that actually teaches the system, and then a novice programmer going in to execute, the actual production program, it's going to be consistent because you're using a library and you're producing the same kinds of programs based off of what the expert bought it. So now let's go over and see how the digital twin is beneficial for manufacturing, but more so how it connects with the digital thread. To explain this topic, because it's a fairly complicated topic, let's go through a very, very simple example of controls feedback. So real, control feedback on a CNC machining process. And then we'll go into real-time control feedback. And then we'll take a look at how we can then leverage AI in that control feedback. So in this example, we're going to use Siemens NX to generate the CAM program to produce the part that you see up at the top left quadrant, or the box. We're going to use a LaserTech 65 system that we have at CCAT to actually machine the part. Attached to that LaserTech system, we have a Veriscan Pico, which is a 3D scanner sensor. And then we have geometric control that's going to be extracting the inspection results. So what you're going to see next is a video of a process that first machines the part, stops before it does the final machining. It grabs the scanner in the spindle, it scans the part, and it helps a very quick inspection result from the current step in the process. It'll identify any features that are out of spec. So you'll see that in just a moment when the inspection report comes up. So here the scanner is leveraging non-contact inspection. There at the bottom, we see that the width of a particular slot was out of tolerance. because it's integrated, it knows what tool was used to cut that spot, and it applies it or an appropriate radius offset to accommodate for the tool wear, and then it re-executes that particular machining program. So the machine goes back, and you saw that right slice hem cut that it did on that last slot, and it's now going to reiterate and inspect that particular part again to verify whether that particular feature has been made in tolerance or has been now measured to be in tolerance. And in this particular case, it is. It would do this 3 times, and if it's not able to get it in tolerance after the 3rd time, it would tell you to change the tool. So what's the benefit here is that you know that you're going to get a good part off the machine. But the drawback is that you're actually extending your machining time. So it's no longer taking you 10 minutes to produce the part. It's now taking you 12 minutes because you have to stop and you have to take a hard measurement and then make a decision off that measurement. So you're gaining a little, right? And you're losing a little bit of time in that. How do we take advantage of the benefits while dropping the negatives? This is where real-time control feedback comes in. So in this example, we're going to use the same DFG machine, and we're going to machine that part that you see on the right. We start off with the stock material on the left. We have the top circuit or pocket that we're going to concentrate on for this particular example. So you can see highlighted in blue, the image second to the left is the feature of interest. The flat end mill is the tool that we're using to produce this particular feature. What we did was we collected the amount of power that the spindle consumed while producing that particular feature. So we're only collecting one data point at a high frequency. So every 2 milliseconds, we're getting the amount of power that the spindle consumed producing that particular part. We cut 18 parts, right? So we had a sample set of 18 parts. And what we can see is if we plot the data on the top there, what you're seeing at the top left is the inspection result of the feature diameter for part number 3. It came out to 1.85 inches. And for part number 12, by the time we got to part 12, it was down to 1.74. So obviously, something is changing the process because the features no longer be produced. It's no longer being produced to the accuracy that it needs to. If we look at the data, you can see the graph at the bottom left. To produce part number 3, the machine actually consumes less amount of power than to produce the same feature for part number 12. In this case, for part 3, we're consuming 950 watts of power. Why? Because we have a sharp tool that's actually cutting through the material more easily than by the time we get to part number 12, where the tool is now dull. You're no longer cutting the material as much, you're actually pushing it. And so it's, by the very nature, it's consuming more power to rotate that tool through the material. And so you see a higher power consumed. On the right, all we have to do, we have 2 data points. We've got the accuracy to which the feature was produced and the power consumed. If we plot those 2 data points, we can fit a line to those 2 data points. And that highlighted equation there, that's our model. The value of the model becomes, the next time I'm producing that particular feature, if I'm consuming 1012 watts of power, I can predict that I'm going to produce a feature of 1.8 inches. This predicted dimension allows me to take corrective action. And we'll see more of that in the next slides. So that very simple example demonstrates the value of adding even one sensor to your machine and what you can do with the data that comes off of that sensor. But in reality, there's a lot of different kinds of features. You can get a lot of different data points, not just the power consumed by the spindle. How do you process all that data? And more importantly, how do you process all that data in real time? This is where we can leverage artificial intelligence because it got so good on data processing. It does so good at recognizing trends, and we can get direct value off of it if we incorporate AI right on sheet. Sorry. This is the overall architecture that really needs to be set up for a beneficial digital plan. What we have is we start off with model-based definition on the left. We can see at the bottom there our IDR or list, some folks call it. At the bottom left, that's our model-based definition, a digital format. So we're starting off with the digital format. Our stock material is next. Any information you can grab off your stock material like hardness, the temperature that it's at before it goes on the machine, grain orientation, that's important. And any other data points that's very easy to grab. If you're starting off with a casting or forging, take a scan of it before it goes on the machine because that can tell you a lot of what happened if the part doesn't perform. Then we have our machine that is connected to an X device. That X device allows us to digitize the process. Then we have our inspection. So long as we're using an inspection system that gives us a digital value, right? Even if you have hand calipers that have a digital readout and connectivity to a central system that is actually recording the value that's on your calipers, that's sufficient. The point here is that from production, from starting from CAD, stock, all the way to inspection, you want to make sure that you have some digital signature coming from each of the components of actually producing the part, because those digital signals feed up into the AI system. The next slide decomplicates what you're seeing here. I'm going to skip over this to show you the high level. What we're doing is we're grabbing real-time data off the machines that's coming from the left. From the right, we're grabbing the result of the manufacturing process, right? So we produce the part, we capture this the signals that were the signature of the signals that are recorded during the production process, and then the result of the production process through the inspection. And we can use AI to create what's called a predictive model. Okay, what I showed you before with the line equation, that's what I mean by model. It's basically a black box where you can feed it the machine data and it will come up with the inspection results. So that model gives us the ability to predict the feature dimension with a multi-dimensional capability. What I mean by that is we're not just relying on machine, the single motor signal, like the power consumed by the stimulus that we're looking at the core. Now we can grab X, Y, Z, A, and C data. We can grab actual axis position. We can graph it or the load on the particular motors and any bits of information that the machine controller can give us through the edge device or through external sensors that we incorporate on the machine. What that does is it enables our machining process can now be controlled or have a supervisory control through the use of artificial intelligence. The value here is this. So what I'm showing you here is the result of capturing data and predicting the feature dimensions. What you're seeing on the right is a part that was produced on a machine that is currently still sitting on the machine. And before we inspect it, we can already get the deviation results even before we ever even take one card measurement value. We do that by taking the real-time data from the edge device, pushing it through our predictive model, and coming out with the results that you see on the right. You would normally do this in real time though. As you're producing it, you're coming up with those results and you're using those results to provide corrective action controls. So corrective action controls can be tool radius offset compensation. You can have spindle speed and feed rate override. If you go as far as actually changing the program points, you could do that, but we also just stick with feed and speed override, TOES offsets, NATSEAL offsets. So the value that you can get out of the digital twin is the control of manufacturing variability. You can significantly reduce or even eliminate scrap. If you have a batch of 150 cars that you have to produce, digital twin will almost guarantee that every single one of those 150 parts are gonna come out in spec. Decrease machining time and increase part quality with adaptive control. If you wanted to extend the life of your tool, instead of only producing 50 parts and then swapping on a tool, you may be able to produce 60 parts. Because we can continue using tools that are worn, compensate for that tool wear and still produce good features, we can extend the life of that tool. But through the optimization software that we saw on the visual thread side, we can actually eliminate force spikes to avoid the fluctuating courses that we'll see that cause them to feel burned. So that's a lot to take in, right? We talked about the value of the digital rack. We talked about the value of the digital twin. What does it mean to you, and how do you see it beneficial for you, for the parts that you create, right? For the processes that you're executing in your manufacturing facilities. Introducing a CCAT autonomous manufacturing cell. At our Advanced Technology Center, we're setting up a system that you will have available to you to test both of these processes out, the digital thread and the digital twin, and how it can really impact your processes. This is an overview of the cell. We're going to have AI and machine learning incorporated. We're going to have a product lifecycle management solution. We're going to have an MES system, and then we're going to have a lot of sub-cells that are all connected to edge devices, feeding real-time data back to the AI system, and then providing corrective action and control in real time. We're going to document what we did to come up with this process. We're going to document all of the technologies that went into the cell for your benefit so that you can save time in implementing processes like this. The objective here is to empower regional manufacturing with state-of-the-art technologies, is to establish a hub for research and development, is to enable testing and demonstration of this key technology, particularly how AI could be beneficial to manufacturing. And then we want to create packaged solutions for the immediate adoption of the supply base. The key technologies in autonomous cell will be data collection systems, artificial intelligence, machine learning, digital thread workflows, process digital twins, and adaptive control systems. As part of the package solutions, we're first going to concentrate on what we're calling autonomous CNC manufacturing, autonomous dimensional inspection. You can actually, is one of the systems here in front of you, we brought it. So if you have questions, please do ask. We are going to look at autonomous visual inspection, welding, assembly, and deburring. Those are the first couple of sub-cells that we'll be concentrating on. This is what I mean by package solution. So we're gonna work now all the software and how they communicate together. We're gonna develop the workflows for the digital thread. We're gonna integrate all the necessary hardware together. We're gonna have the training through the digital thread lab of how you can upskill your workforce to effectively use these technologies. And then we have grants available through the state of Connecticut to help you adopt these technologies to reduce your costs, reduce your CapEx. It's essentially half-off for most of the RAP programs that are available and top of policy of the technology. So to reiterate, all the resources available to you, I described digital, correct? Digital twin. Our purpose as CCAT, as your applied R&D center, is to really drive the adoption of the technology and to measure the impact. Because if we get the impact that you're receiving, we can then improve upon the technology with our tech partners and get you in a even better, get you with even better technology leadings of the future. So some of the resources available to you, we have a video library. Everything I described, Siemens solutions, visual proponents, we've got the CMM module. We have detailed step-by-step instructional videos that are available on demand to your workforce that they can log into the CCAT website and gain access to these videos right away. If you want to start to use these processes, they're there for you as a resource. We have our digital transformation programs, a funded program. If you want to learn more about these technologies, please reach out. That's a projects that we can do at no cost to you. We have an additive technologies program, and then we have our talent and training accelerators. The digital Fred Lab at Pickens Street, where you can actually learn, get hands-on, multi-day exposure to these model-based specific workflows. And then some of the grants. I just want to reiterate here that it's very easy to get started on the grant. Literally 3 steps. There's only a few requirements, and most companies qualify. It's money that the state of Connecticut is giving to you to help you, adopt these technologies. Please take advantage. With that, I welcome you to come and visit us. We're your applied R&D center, right? If you ever wished you could have, machines in excess of, $10 million, if you wish you had experts on staff that were just concentrating on looking at, where technology you've been implementing today, also like 5 years, that's what we're here for. We're your team that you can come to and rely on. We're a neutral party. We don't sell anything. And like I said, we can direct you to money that's available to you to help you with adoption. Thank you so much for your time. I appreciate it. Any questions? We're here. We do have a demo of the 3D scanning technology here, and also additive technologies, as well as information about the digital Fred Lab. Thank you.